Hey folks, we're going to try another static torque problem just to see a slightly different situation than the previous one. In this one, the setup is we've got a hungry bear that has a weight of 700 newtons, walking out on a beam trying to retrieve a picnic basket that's hanging here, and it's a pretty big picnic basket. It's 80 newtons, and the beam is a total of 200 newtons. This cable here, we're told, can withstand a maximum tension of 900 newtons before breaking. So how far out can the bear walk? Can he safely make it to the picnic basket is the question. So what we're going to do is start by labeling all of the forces at their point of application. When we start with a beam, it's 200 newtons, but for the purposes of a torque problem, we want to draw that acting at the center of mass, and that's 200 newtons. I don't know the radius yet because I don't know where my axis of rotation is. I haven't yet decided that. Now another force will be the food basket, which we already know is 80 newtons, but I'm going to draw that as a force. And the bear, well, I don't really know where the bear is. I drew him there. Put this label here so I can draw one for the bear. The bear is 700 newtons. Just for clarity, I'm only labeling the amounts instead of mg, mg, and mg and getting confusing there. Now the tension, it says it can support a maximum tension of 900. How much tension there will actually be depends on where the bear is. But to find the maximum distance the bear can go, we will just plug in the maximum value of tension. That's at an angle. It's 900 newtons. Now there's other forces happening here. The beam is attached to the wall here, and the tension has got a component pulling this way, so I know the wall must be pushing outward on the beam, and it may be pushing up or down a little bit as well, and I don't know that amount. So what I'm going to do to get around that problem is I'm just going to make that my axis of rotation. So any forces acting there have no radius, or no radial arm distance, so they are not going to exert a torque. And that very conveniently gets that problem out of the way. Now all I've got to do is write a net torque equals 0 equation. My clockwise torques equal my counterclockwise torques. And let's see, what's clockwise? If I picture the beam here, things pushing downward on the right of the axis of rotation, we'll try to push it clockwise. So now that I've decided on my axis of rotation, let's go back and just figure out what the distances are along that radial arm. Radial arm is extending this way. So the center of mass is halfway out the length of the beam. Oh, I didn't label the length of the beam from the problem this came from. That was 6 meters. That's kind of important. Okay, so center of mass for this uniform beam is going to be 3 meters, and then the basket is 6 meters because that's hanging from the very end, and the tension is being applied at 6 meters also because it's attached at the very end. There, that makes a lot more sense. The radius of where the bear is, that's what we're looking for. So that will be our unknown. So clockwise, let's see, we've got the weight of the beam, that's 200 newtons times the radial distance is 3 meters, so 3 times 200 plus, I'll do the basket now because I have a number for that. That's the radial distance times that force is 6 times 80 newtons plus the bear, R. I don't know what that is. That's what we're looking for. Times 700 newtons equals, now my counterclockwise torque is only the tension. I've got to be careful here because the tension is acting at an angle, and the part of it that is exerting a torque is the part that is perpendicular, or the vertical component of it. So I'm going to have to write that as the radial distance 6 times 900 is the maximum tension, but I'm only looking at the vertical component, so I've got sine 60 in that place. Now if I solve for this equation for R, I'm going to get R equals 5.13 meters. And sadly, the bear does not make it to the basket. If you were to walk any farther, then we will exceed the tension and everything will break, and that will be bad. What would happen if there was more than enough tension to support that bear? Well, very simply, we would get an R value that is greater than 6 meters. The bear couldn't physically be there, but that would tell us, of course, that there's more than enough tension. But not in this case, sadly. Sorry, bear.